Well, Mr. Thompson here with a math video lesson. Continuing on with probability and talking about estimating probabilities. Looking at things where there's not so much of a finite sample space and just straightforward calculations. So subjective probabilities, talk about what those are. Look at probabilities from data and probabilities from area. All right. Table of contents in the description, so on and so forth. So subjective probabilities, what are they? They are basically when you might just make a bit of a guess or an estimate of what's going to happen based on your experience. So we see this often in like sports or people just talking about, making random predictions and things like that based on what you've seen happen. For example, sports commentator might be on TV talking about an upcoming match and saying they think that a certain team has 60% chance, or whatever number it may be, chance of winning, right? They would say that based on what they've seen the team doing maybe so far in the season and what shape the players are in and what the grounds are like and whatever else, things like that. So it's based on experience, but ultimately it is a bit of a guess, right? You might say something like your neighbor has a 40% chance of forgetting to put the bins out. Maybe you've noticed that, a certain morning in the week they're running after the garbage truck or whatever it is because they forgot to put their bins out, right? Now, most of the time, these are some form of a guess, or sometimes they can be a guess, and sometimes they can be based on actual calculations. Maybe you've observed your neighbor and how often they forget to put the bins out. And you have hard data saying, well, this is what they've done in the past, so any given week, these are the probabilities. So let's look at how you might go about doing some of those calculations in order to make accurate estimations. So in order to increase the estimation, you can use data and you can do experiments to base your guesses and your estimations on the numbers that you find. Okay, so when we do this, what we're finding is the relative frequency. So the relative frequency is calculated much like the probability of things with, random experiments with equal outcomes. Relative frequency is found by dividing the number of times an event has happened, right? The number of times it's occurred, divided by the total number of trials, or what we might say is like the total number of opportunities that event had to happen, right? How many times did it happen out of how many times it could have happened, right? And we'll look at some examples of this in a minute. We do need to add a note that sometimes experiments on certain events, maybe you can't directly test a certain outcome, right? But you can create an experiment with similar outcomes, and it can be run as a simulation, okay? So one example of this is climate change, right? Where there are so many different factors, and we can't like set up various Earths and run different experiments and see what happens with climate change over long periods of time. So we have to develop mathematical models or experiments that are similar to what's happening to then predict what can happen in the future, okay? So let's look at some examples. So we've got your friend is flipping their bottle, right? Throwing their bottle up in the air, it's flipping around, and they're trying to land it on the table. Unlike a coin flip, right? There's not like a straightforward, calculation you can do to say, well, the chances of it landing are X, right? Or this or that, right? It's not a symmetrical object. It doesn't just have one side or the other. There's all kinds of different ways it can land. So we can't just say, oh, it's 50-50 or 25% or something like that. What we're going to do is run the experiment. We're going to get your friend to flip it over and over again and see how good they are at doing it, right? So what if they flip the bottle 10 times and they land it only once, right? The relative frequency would be that one time they landed it divided by the 10 times that they tried. So 1/10, right? 1 over 10. And I'm going to write these all as percentages, okay, so that we can compare them directly. So that would be 10%, right? Well, what if they tried it 50 times, right? And out of those 50, they land it 6 times, right? That's a little bit better. 6 out of 50, we can simplify that to be 3 out of 25, which again, we convert to a percentage, and it's about 12%, right? It's exactly 12%, that is. And so, yeah, a little bit better than the 10% they did before. So, but what if they did it 100 times and they land it 11 out of those 100 times? Then the relative frequency would be 11 over 100. The percentage, of course, is 11%. So different percentages with a different number of trials, because what happens is that we increase our accuracy, right? The 10% wasn't too far off. 12% is different, but we start to hone in on what the actual, the more accurate estimation is as we increase our number of trials. And that brings us to a really important principle, that when we're running these experiments or collecting data, the higher number of trials, the more data we have, that will increase the accuracy of the estimations, okay? And what we say is that the probability of the probability of event A happening, is approximately equal to the relative frequency of A for large numbers of trials, right? So the more trials we do, the closer we're getting to an accurate representation of the actual probability of A happening. That little squiggly equal sign, of course, means is approximately equal to, or that kind of thing, okay? So to increase your accuracy, more and more trials. That's why when we see scientific studies and polls and things like that, we need to have a certain size of our sample space, right? All right, one more thing here, one more note, that we can do probabilities involving area as well. So when the best way to explain this is really through an example, right? So imagine somebody's throwing at a dartboard, and it says here randomly, right? So it's not like somebody that's really, really skilled and has practiced heaps or whatever. Let's say they're even maybe covering their eyes and they're throwing darts at a dartboard, all right? And also we're going to ignore the darts that miss the board entirely. So if it hits the board, assuming it hits the board, what are the chances that it hits the bullseye, the red bullseye, right? To do this, what we're going to do is find the area of that red bullseye, okay? So that's step one. Area of a circle is pi times radius squared. The radius of that red circle is 2 centimeters, right? So it's pi times 2 squared, which comes out to about 12.6 centimeters squared, right? The next step is we find the area of the entire target, right? So same thing, pi r squared. It's going to be pi times 5 squared. And so we get about 78.5 centimeters squared, right? And then finally, what we do is we find the ratio of those two areas. So we divide the area of the bullseye, the thing we're interested in finding that probability for, by the entire thing. So 12.6 over 78.5, which equals about 0.16 or 16%, right? The centimeters squared, if we added them on here, they would be on each of these and they would cancel, right? So there's no units for our probability. It's just 16% chance of that happening, right? Okay, some different ways to estimate probabilities, subjective probabilities. Hope that helps. Catch you next time.